Hi, welcome to the Vector Virtual Timing Day. Now following up with the presentation Cleaning Timing Pitfalls on MICROSAR Classic projects. I'm Christoph Stuhl, I'm a cleaner for MICROSAR projects, and let's deep dive into the topic. First, let me tell you something about my background. I'm originally a chemist, and I would like to bring up the idea now in your head, the imagination, how does a chemistry laboratory look like? What comes into the mind of the people are pictures like this. So you have these clean workbenches and this clean laboratory, and there are these scientists wearing these white coats working in those facilities. Now, reality looks different. Let me show my lab back in that time. So you see a lot of different containers in here, and this big pile on glass vessels was my mess. I spent most of the time actually not doing chemistry itself or making new substances. I spent the time with cleaning. So you rinse these containers, you scrub them, you dry them, and this takes most of the daily routine. Now, let's check your home. Imagine now your bathroom or your kitchen. How often do you clean your space at home? Does your bathroom every time look like this? Is the sink of your kitchen always as clean like this? You don't have to tell me the secret about this. You can keep it in private. Just think if it's always representing that state. Let's go to the automotive industry now. I have a simple ECU again for you. Imagine this could be any ECU on the market. Would you buy or sell this ECU if you do not know how clean your scheduling looks like? So, two possibilities. Imagine you have a scheduler, your CPU load is pretty high, always at 100%, or you spend some effort, you cleaned your scheduler, you can show, you can prove that you are in a very good condition in here. Let's discuss as introduction a short methodology how to perform a scheduler cleaning, very simplified. Step one, you specify a timing constraint called Timex. To keep it simple, let's put in a simple statement in there. A 5 millisecond runnable shall run every 5 milliseconds. As step two, you follow up a timing bundle integration. You can get these timing bundles offered by Vector accessing this link and integrate this on your ECU. And this is an enabling package for you to be able to recording a schedule trace. In step three, you can run a data analysis on it with the Timing Architects tool suite and generate out a report, now proving that your Timex constraints, 5 millisecond runnable runs every 5 milliseconds, are fulfilled or not. And if you see any check conditions in the red state, you start your actually cleaning procedure until your report is green and your overall criteria is matched. That being said, I brought this time two more timing pitfalls, the initialization phase and the scheduling phase of your ECU. Let's go to pitfall number 5, the initialization phase. So my multi-core sandbox project I brought you for this presentation is pretty simplified. You have a 6-core system where the applications of the components are integrated on each core. We have a communication stack up and running, so a multi-instance CAN feature is integrated. CAN 1 is running on core 0, CAN 2 is running on core 1, an Ethernet stack is allocated on core 2. So we have quite a good playground to play around with different runtime scenarios. So, my colleague Hossam was preparing this demonstrator for me to work on, and I asked him to prepare everything. So, investigating core 2 to core 0, everything runs, but I was interested on working on core 5 and run into problems and started with the debugging. So, from a perspective, Hossam's argumentation was like, the scheduling runs on my machine, but my answer simply was, it's not running on my machine, it's crashing. And you see, actually, when we investigate all the 6 cores, that core 0 to core 2 behave differently, show a different behavior than core 3 to core 5. Now, let's try to understand what's going on. So, somehow it seems that the init tasks are running before, then they put in an endless state, and these interrupt service routines from the counter ISRs are never finishing. Of course, we hit an error hook, and the error returned here is called OS status limit. You may be familiar to this error, and you faced it in previous projects. Let's fix it by now. So you see, by simply returning the error hook routine, my system is back up and running again, and I fixed a clean startup now and can work on my project. Stop. Please don't do this and include it in your project. Do not directly return from your error hook routine. This is an insurance that you will face an escalation in the upcoming project phase. What happened? Do not modify the error hook. Try to understand the errors, what is actually going on, and try to then fully understand the issue and by integration steps resolve it. Let's do this for the OS status limit error. Let's try to understand what happened. Actually, in different words spoken, a task has been activated too often. If we check the configuration of this project, we see we have this alarm for the ECUM main function running on core 5. And as alarm action, once the alarm expires, we want to activate a task. This is exactly happening on core 3 to 4. The alarm is being set, expired the first time here during my initialization phase. And exactly after 10 milliseconds, the task is being activated again. But since we were still in the init task, we had not been able to schedule the ECUM main function in the respective task. We are observing this error. Now we fully understand and found the explanation why this error is happening. Let's fix it. So I'll present you now 3 ideas how it potentially could be fixed. Please note that there is maybe a trade-off for your project, so it's not directly applicable. You still have to judge if this is a way you can go for it or not. One option would be we change the alarm action on expiry from activate task to alarm set event. Because if we are setting an event during an expired alarm, then which is already being set, we will just miss the cycle of the main function because the event is already being set. We do not see an error hook. I implemented this for core 3 and core 5. Core 4 is still the original state. Here you see nicely 3 and 5 are running, so the OS ISRs can be seen, and core 4 is still hanging in the error hook as reference. Let's find another fix. We can add a 10 millisecond initial offset. So what will happen in here is the first expiry of the alarm is shifted by 10 milliseconds. Again, you see this in here. The first instance on core 4 is now expiring in here, and from there on we have 10 milliseconds time before the next alarm is expiring. So the ECUM main function the task itself should be called in between, therefore the ECUM main function. Also here you see all the 3 cores are running back up again, so we resolved the error hook by not touching its implementation. Please keep in mind there is a short trap behind it. If we are not able to schedule the main function and the task till here, this point, we observe the same behavior and the OS status limit is hit again. So this implementation is not rock solid. It can change if you add up more functionality during your initialization phase. Step 3, the third idea would be to resynchronize the alarms again. So let's assume we are canceling the alarm during the startup in here because we're busy with some other tasks. We want to do some other initializations. And at the very end of our project, of the initialization phase, rightly before we start with the normal scheduling, we set the alarm again. And also here you see this nicely 10 milliseconds pattern now of the ECUA main function. So I like this in scope of symmetry because in comparison to core 3 and 5, you see here the ECUA main function cyclicity of 10 milliseconds is not exactly matching in here. So my rationale 7 for you is check your alarms and your task types, basic versus extended, and you may identify an issue in your initialization step, leading finally to OS status limit, and you are able to resolve it then. Of course, this is a sandbox project. Let's have some fun. So I brought a challenge for you, how to synchronize 36 init tasks on 6 cores, if this is achievable or not. So imagine we have these 6 runners in here, and I would like to show you now the effect of OS barriers as synchronization points, how it could influence your startup behavior in your project. So for the sake of clarity, I had to omit some of these initialization tasks, but in total it's 36. And here you see 5 cores in parallel, and this long black bar is each core's idle task, meaning the initialization phase stops, was ending, completed during these points in here, and here the normally scheduling phase starts. I sort these init tasks in the order of, for example, basic software ASIL and QM tasks, application software basic and QM tasks, some default init tasks, and you see each of these tasks are assigned a random runtime to it. So this leads to the case that the scheduling phase is not synchronized. So the startup is finished on each core completely independently. And this gives some room in multi-core projects already for some errors. Because in this case, you gain, for example, you start the scheduling and you're depending on some variables. They need to be initialized on another core. So I think it becomes quite clear for you what kind of errors you're dealing with, and you may have such experience from past projects. Let's see how we synchronize each of the init tasks with OS barriers. So here you nicely see you're switching to each init task at the exact amount of time. So I simply used the barriers at the end of the init tasks. The trade-off here becomes pretty clear. The overall execution time is adding up. So you start your scheduling at a very late point of your project, but it is at least fully synchronized. So each of those tasks are running synchronously, and scheduling starts at the exact same point of time on each core. We can remove some of these barriers in case we are only interested to synchronize this last point, and that way you do not care about the execution time of the init tasks, but you're interested that the scheduling point here starts at the exact same point of time. So let's call this a partly synchronized startup. So my rationale 8 for you is use the OS barriers in your project to remove barriers, blocking points, synchronize your startup, actively take care about this, and try also to undermine this with meaningful traces. Now, since we dealt with the initialization phase, let's come to my pitfall 6 for you, the scheduler. And in this case, I would like to come up with another example project. So here we are having now a scheduler component. This one has some random runnables. I call them 1 millisecond, 5 millisecond, 10 millisecond runnables. And the runtime I'm simulating by simply calling some knobs, and the amount of knobs differs in each runnable. So we have here random mapping and the runtime mapping to tasks and the random runtime. And in total, it's this amount of runnables you can see here. I integrated them on Core 5 and distribute them on these kind of application tasks. So let's see what comes out after I did my first measurement of this project. It looked like this. So you may immediately seeing notified some issues. So question from my side is, how many issues do you find in here? As help for navigation, I provided this color map for you. So orange means this task is in waiting state, dark green means this task is currently running, and the light green area means the task is in the ready state, so it would like to run, but it has to wait till higher priority tasks are finished. And if you're familiar with the scheduling system and when you start working on it, let's see what we can identify and mismatches. So point number one would be, from my side, we see a lot of task activations, especially on the highlighted points. You see up to all tasks are activated at the same point of time, and this is causing maybe additional runtime overhead for your project. So we also observe a missing task execution at all. So this 1 millisecond task and this 10 millisecond tasks, they always stay light green, so they are never able to run. And here, based on the observation of the trace, I already would observe some errors in your functionality from the ECU, even if it's not running stable. What is also obvious, the task periodicity of this task looks a little bit strange, because the name of this task is 5 milliseconds, but you see this task is running each millisecond. So let's find out how we could easily track this. So with dimension timex, you can define an individual amount on constraints, and these constraints can then be checked through an analysis tool, the Timing Architects tool suite, with the inspection feature if you are sticking to these constraints. For example, here we're calling the start to start metric, and you see how many occasions are counted in the trace and on how many occasions you are violating this constraint. And you see we are not matching the start to start constraint of the 5 millisecond runnable and of these 1 millisecond tasks, respective to runnables. And some of these runnables are not even in the trace. That's why they are marked with that blue question mark. So let's deal with the first issue. Let's do a little bit of regrouping. So let's now assign all the 1 millisecond runnables to the 1 millisecond task, the 5 millisecond runnables to the 5 millisecond task, and the 10 millisecond runnables to one task. This immediately seems to be beneficial for our project. So you see this in a way more clearer way now. We still have this missing task execution, but I see my task activation is resolved because maximum I'm activating 3 tasks at one point of time, and the task periodicity is partially correct, but let's see what we can do as a next step. So in this case, you see the 1 millisecond task is not able to run. It's prevented by the 10 millisecond task. Let's re-switch the priority. Also check the revealing timing pitfall series for that. If we give the 1 millisecond task a higher priority, you now also see how this pattern further clears up, and we do not see an issue in here right now. As a last step, tip from my side, what we could do, since we only have a 1 millisecond, 5 millisecond and 10 millisecond periodicity on each task, in this special case we are now also in the position to switch the task type back to basic, and by switching it back to basic we gain a little bit more performance boost out of it, and now you see a clear scheduling happening in here. Back to our timex, it's not a problem anymore, so you see not a single violation on this project any longer. The runtime was always untouched of the runnables. It was simply optimization by remapping, reassigning the runnables to tasks. So to also show this in another way, this was the initial stage of the project, where you see a lot of different and long ready states or tasks which are even not running or not able to fully finish. Once we redo the mapping, you now see everything is being placed correctly and the runnables are able to run in order, in its logical orders. That being said, Let me give you 2 more tips for it. Be aware of the number of tasks in your project and always monitor the timing constraints which are applying to your project. So, as end of the presentation, I would like to bring you a customer project. So here we did really a hands-on cleaning. The first impression was we are seeing the OS counter interrupts in here. We see some core synchronization done in here. And below I brought 2 tasks where you see the scheduling is pretty dense and we try to activate those tasks very oftenly. Let's start by cleaning it systematically. So first we worked on the timer interrupt service routine to make the OS counter in the right periodicity and verify this once. At second point, then we started to work on the core synchronization. So here we adjusted something in the design, and the task scheduling now was the last part we took care about. And here we did the architectural optimization, further reducing the runtime in here, and you clearly see how the project clears up. So we consider this as a success story, and to show you the initial state and the end of this work, you clearly see a big impact with 3 easy steps. So we identified 3 different locations and at once and had been able to clear them up one by one. To show this with another figure, we had analysis level 2. So we introduced only the task and the OS scheduling in here. This was a period of 4 months in a vector coaching mode in a dual core system. And as an output highlight, you see the initial CPU load on both cores from 99% was further decreased to 28% on core 0 and to 54% on core 1. So the very benefit of this approach is with that loads on each core, it's a really strong base for the next generation ECU of this project. Finally, I would like to thank you for your listening now and open for discussion round. Please check the rationale 1 to 5 in my other videos in here. For this presentation, I brought you now 5 more tips you can apply immediately on your project. So don't return from your arrow hook. Check your alarm action and task types. It may help you to understand OS status limit and fix it in your startup phase. Use barriers from the OS to remove barriers during the startup. Check the number of tasks you can reduce them and condense them. And at the end, monitor your timex. In the case you would like to achieve the same or similar results in your project, ask Robin and Florian for workshops and coachings. You see the contact details in here. Check out the vector timing bundles. They are provided on the homepage. You can start with the integration right now. And I'm looking forward for the technical discussion and see you in the future. What was the point about the introduction? So I presented you this mess in the laboratory I have to take care about and be busy with always cleaning and cleaning. And I showed you this return from the arrow hook routine, how it could cause issues in your project. So you may check it if you find some piece of code in this. If that's the case, you may need a cleaner. So you can ask for a vector cleanup coaching service, and then we may figure out how we can fix your project. Thank you for your attention and see you next time. Goodbye.